Hello everyone. So today we will study convection in turbulent flow. Most flows in nature and in industrial applications are turbulent. You will find applications in mixing of the flows, then in combustion processes as well as in heat exchangers. Generally turbulent flow occurs relatively at high Reynolds number, and in turbulent flows velocity, temperature fluctuate with time. Turbulent flow is a complex physical phenomena. Turbulent flow is disordered with random and unsteady velocity fluctuations. In laminar flows, we already had the exact solution of many flows with certain assumptions, but in turbulent flows it is very difficult to have the exact solutions. So, mostly whatever correlations we will write, that depends on the experimental values, and that is why we will write the empirical correlations. You know about the famous experiment carried by Reynolds. So, you can see here Reynolds did this experiment. So, the ink is injected here in a tank and this is the pipe. When it passes through this pipe, you can see this difilament is almost straight line. You will get this type of flow when you have low velocity, but if you increase the velocity here, then you can see this difilament will diffuse in other directions. So, it is due to the fluctuation of the velocities at high Reynolds number and it becomes turbulent flows. So, you will get this kind of structure. You know that in pipe flow, when Reynolds number based on the diameter is less than 2300, then it will be laminar, then it will transform to transition and turbulent flow. If you consider flow over flat plate, which already we have done the exact solutions in earlier classes in external flows, you have seen that near to the leading edge of the flat plate we get laminar flows, and we have done the study of this laminar flow. But if you increase the length, then you will find that it will become a transition regime, then turbulent. So, you can see here, say you have a free stream velocity u infinity, when it will come and flow over this flat plate. So, obviously you know, due to the viscous effect there will be formation of boundary layer, and near to the leading edge you will get laminar flows. Okay, you will see that very streamline flow, but after that there will be some disturbances near to the wall and it will propagate away from the wall slowly, and after if you go ahead and you will get a fully turbulent flows. Okay, and in this case you see, if Reynolds number based on the length of the flat plate, if it is less than 5 into 10 to the power 5, then you will get laminar flows. Okay. So, turbulent flow is very complex and chaotic. So, it is very difficult to define turbulent flows. So, most of the researchers, they have given the characteristic of the turbulent flows. So, you see, turbulence is comprised of irregular, chaotic, three-dimensional fluid motion, but containing coherent structures. So, you can see that turbulent flow inherently three-dimensional and unsteady, okay, but with certain assumptions again we may consider as two-dimensional flow as well as steady flow. When we consider the velocity components or temperature as comprised of mean value, time averaged mean value and the fluctuating components. Turbulence occurs at high Reynolds number where instabilities give way to chaotic motion. We have already seen in external and internal flows, obviously it is a high Reynolds number flow, then the turbulence occur. Turbulence is comprised of many scales of eddies which dissipate energy and momentum through a series of scale ranges. The largest eddies contain the bulk of the kinetic energy and break up by inertial forces. The smallest eddies contain the bulk of the vorticity and dissipate by viscosity into heat. So, you can see that in general you will have a larger eddy which will contain bulk of the kinetic energy and it will be transported by the velocities, and during this transport it will divide into smaller eddies, okay, and it will keep on decreasing the size of the eddies, and those eddies will contain bulk of the vorticity, and then it will actually dissipate into heat by the viscous effect. Turbulent flows are not only dissipative but also dispersive through the advection mechanism. So, when we study the turbulence, we make two common idealizations, one is homogeneous turbulence and another is isotropic turbulence. What is homogeneous turbulence? If the turbulence has the same structure quantitatively in all parts of the flow field, then the turbulence is said to be homogeneous turbulence. And in isotropic turbulence, the statistical features have no directional preference, then it is called isotropic turbulence. So, when we do the numerical simulation of these turbulent flows, we need to have some prediction methods. So, here you can see, as we discussed, you have a large scale eddies, let us say its scale is of the order of L. So, it contains bulk kinetic energy. Due to the inertial effect, okay, it will be transported, and due to the during the transport it will divide into smaller eddies, okay. Then again it will become smaller, 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 and after that it cannot be smaller than this eddy, and that time this eddy will contain bulk of the vorticity, and this vorticity or this eddy will dissipate heat due to the viscous effect, and the scale of this eddy is known as Kolmogorov scale, and eta is known as Kolmogorov scale, and Kolmogorov scale is equal to L divided by Re to the power 3 by 4. So, you see Re is based on the large scale eddy length, and if Reynolds number is very high, then eta, which is your Kolmogorov scale, will be very low, and to actually compute or to capture these smaller eddies, it is very difficult, because you need to have very small grid size to capture this small eddy. So, you can see, if you solve the Navier-Stokes equations using direct numerical simulation without modeling any of the eddies, then you need to have very fine mesh, okay, so that you can capture the smaller eddies, okay, in the Kolmogorov scale length scale. Now, direct numerical simulation for 3-dimensional flows and unsteady flows, obviously it is very difficult, computational time will be huge, and generally for industrial fluid flow direct numerical simulation is very difficult. We can have some smaller scales we can model, and rest of the eddies we can compute using large eddy simulation. So, we can see in the large eddy simulation, up to certain eddy size we resolve and rest we model. And another simplified way to solve this turbulent flow is just using the Reynolds average Navier-Stokes equation. So, whatever velocity and temperature you have, you can decompose into two components, one is time average mean component and another is fluctuating component, and we can solve these governing equations in a average sense. So, here you will model only the large scale eddies, but other you need to model it. Okay. So, in this course we will derive the Reynolds average Navier-Stokes equations, and later we will learn how to solve for flow over flat plate and the pipe flow. You can see examples of turbulent flows in mixing processes, free shear flows, wall bounded flows. So, these are some examples you can see in turbulent jet, turbulent wake behind a body. So, if this circular cylinder is heated, then obviously there will be convection in turbulent flow, and here obviously you can see turbulent wake behind smokestack. So, in the smokestack you will have high temperature and ambient will be at lower temperature, and there will be convection, and that is your turbulent convection you will get. Here you can see the instantaneous velocity profile. So, velocity will vary with time. Okay. So, these are the velocity profile over a flat plate, and if you time average the quantity, then you will get this dotted line. So, you can see this is the time averaged velocity profile, and obviously you will get a smooth curvature of this velocity. And here we have compared the velocity profile for laminar and turbulent flow. So, this is your laminar flow velocity profile and this is your turbulent flow velocity profile. So, you can see in turbulent flow near to the wall you have more gradient. Okay. So, obviously you can see from this velocity profile. Now, we have discussed that these velocity and temperature fluctuate with time, and we can decompose into two components, one is time average mean component and another is your fluctuating component deviating from the mean value. Okay. So, you can see this is some velocity varying with time. Okay. And we can decompose this velocity into two components, one is time average mean component. So, we will denote with u bar and plus your fluctuating component, that is your u prime. So, you can see if we take the mean, so this is your u bar. So, this straight line is u bar, and whatever fluctuating component you have, whatever it is deviating from the mean value. So, this is known as steady mean motion, because your mean velocity is not varying with time, but you can have unsteady mean motion as well. So, here you can see these are fluctuating components. Okay. And if the time period is t1 of the fluctuation, so here if you time average in this period, and you will get that your mean value will also vary with time. Okay. So, in this case you can see that T2 is the time period of mean velocity variation and T1 is the time period for the fluctuating velocity variation. Okay. And you can see here velocity is also varying with mean velocity is varying with time. So, this is your unsteady mean motion. So, Reynolds first proposed that we can have this decomposition of this velocity into two, one is mean velocity and the fluctuating velocity. So, this is known as Reynolds decomposition. So, first we will see that if you take any scalar f and if we decompose into two, then what are the identities we can have. So, if we consider a scalar property f, then we can have f bar, which is your time averaged value, and f prime, which is your fluctuating component. Okay. So, you can see this is superposition of this time average and fluctuating components. Now, if you calculate the mean value, that means it is, if you have a time period tau, then it is defined as 1 by tau 0 to tau f dt. Okay. So, this way actually you calculate the time average component. So, you can see in this case that if you put this f as f bar plus f prime, then what you will get. So, now f bar we can write as 1 by tau 0 to tau. Now, we are substituting f with f bar plus f prime, then what we can have. So, you can see, so f bar which is your average quantity. So, you can bring it outside the integral. So, f bar 1 by tau 0 to tau dt. Okay. So, we assume that in that time period f bar is constant. So, you can take it out of the integral and we can have 1 by tau 0 to tau f prime dt. Okay. So, you can see you can write f bar. So, this 1 by tau 0 to tau dt will give only f bar, and what does it mean? This actually give the definition of this average quantity, that means it is f prime bar. So, you can see this quantity and this quantity are same. So, you can see f prime bar is 0. Okay. That means time average of the fluctuating component is 0. So, time average of the fluctuating components is 0. Now, let us consider another scalar property g, which is your g bar plus g prime. Okay. So, if you calculate f bar g prime, what does it mean? F bar, so g prime is g minus g bar is equal to f bar g minus f bar g bar. So, if you take the time average of this quantity left hand side, then what you will get? So, you will get f bar g bar minus f bar g bar bar. So, you can show that this quantity will be your f bar g bar and this quantity also will be f bar g bar. So, this is equal to 0. So, you can see f bar g prime average will be 0, and now if you calculate f g, that means f bar plus f prime g bar plus g prime. Okay. So, what you will get? F bar g bar plus f bar g prime plus f prime g bar plus f prime g prime. Now, you take the time average of this quantity. So, if you take the time average of this quantity, so this will give f bar g bar. Okay. This will give f bar g prime bar plus f prime g bar plus f prime g prime bar. Okay. So, you can see this quantity already we have shown that it is 0. So, this is 0 and this is 0. Okay. So, you will get f g bar is equal to f bar g bar plus f prime g prime bar. Okay. And if you write f square, so from here you can write f bar square plus f prime square bar, and f prime square bar is not equal to 0. Okay. F prime square bar is not equal to 0. The time average of the fluctuating component is 0, that we have already shown. That means f prime bar is equal to 0, but f prime square bar is not equal to 0. Why? Because this is a fluctuating component. So, it is the deviation from the mean value. So, it is having the positive value as well as negative value. So, but f prime square where when you are making, so it is always positive. So, f prime square bar is not equal to 0. So, now you can see the general properties of turbulent quantities. So, if we have two scalars f and g, and we have f is equal to f bar plus f prime, g is equal to g bar plus g prime. So, you can see time average of f bar will be just f bar, f prime bar is equal to 0, that we have already shown. Then f bar square bar will be also f bar square, but f prime square bar is not equal to 0, and f bar f prime bar will be equal to 0, that we have already shown. F square bar is equal to f bar square plus f prime square. So, that also we have shown. Now, if you take f bar g bar whole bar is equal to f bar g bar, f plus g bar is equal to f bar plus g bar, f prime g prime bar not equal to 0, and f g bar is equal to f bar g bar plus f prime g prime bar. Okay. And if you take the derivative, okay, s is any spatial direction, then del f by del s bar will be del f bar by del s, del f prime bar by del s is equal to del 2 f bar by del s square is equal to 0, and del f prime g prime by del s whole bar is not equal to 0. So, now these properties we can use for the when we will decompose the velocities and temperature into mean quantity and the fluctuating component. So, first we will start with the Navier-Stokes equations. We will write the Navier-Stokes equation in weak conservative form. So, you can see if you consider two dimensional steady state incompressible flow with constant properties. So, in Cartesian coordinate you can write continuity equation as del u by del x plus del b by del y plus del w by del z is equal to 0, x component momentum equation del u by del t plus del u by del x plus del u v by del y plus del u w by del z. So, this is your convection terms, and you can see we have written in weak conservative form. Okay. So, if you invoke continuity equation you can put from non conservative form to this weak conservative form, and in the right hand side you will get minus 1 by rho del p by del x plus nu del 2 u by del x square plus del 2 u by del y square plus del 2 u by del z square. Okay. So, this is the diffusion term. So, this last term actually you can write also nabla square u. Okay. So, in the bracket whatever quantity is there, so you can write nabla square u, because you know nabla square is del 2 by del x square plus del 2 by del y square plus del 2 by del z square. Okay. Similarly, y momentum equation you can write in conservative form. So, this you can write in conservative form u v w. Okay. So, this is in conservative form is equal to minus 1 by rho del p by del y plus nu gat square u v, and z component momentum equation also is written, and this is the energy equation in weak conservative form. Okay. So, right hand side is your diffusion term, we have neglected the viscous dissipation, and alpha is the thermal diffusivity, and obviously nu is your kinematic viscosity and rho is the density. Now, we will use the Reynolds decomposition. So, we will write the velocities u, v, w and temperature T as superposition of mean quantity as well as the fluctuating quantity. So, we can use u is equal to u bar plus u prime, v is equal to v bar plus v prime, w is equal to w bar plus w prime. You have pressure, so P is equal to P bar plus P prime, and temperature T is equal to T bar plus T prime. So, first let us consider only x momentum equation, okay, and we will do the derivation, and similar way you can do for the y and z momentum equations. So, we have the continuity equation. So, continuity equation is del u by del x plus del v by del y plus del w by del z is equal to 0. So, if you substitute u as u bar plus u prime by del x plus del v bar plus v prime by del y plus del w bar by plus w prime divided by del z is equal to 0. So, you can write it as del u bar by del x, del v bar by del y plus del w bar by del z, and you have del u prime by del x plus del v prime by del y plus del w prime by del z is equal to 0. Now, you take the time average. So, taking the time average, we get, so you can see if you take the time average of del u bar by del x bar, so it will be equal to del u bar by del x only. Okay. So, this will be del u bar by del x. Okay. We have already discussed these properties, right. So, you can write del b bar by del y bar is equal to del b bar by del y, and this you can write del w bar by del z. And if you take the time average, then you can write del u prime bar by del x plus del v prime bar by del y plus del w prime bar by del z is equal to 0. We have already shown that the time average of the fluctuating components are 0. So, that means u prime bar is equal to 0, v prime bar is equal to 0, w prime bar is equal to 0. So, that means these quantities will be 0. So, this will be 0, this will be 0, and this will be also 0. So, you can have del u bar by del x plus del v bar by del y plus del w bar by del z is equal to 0. So, you can see the time average velocities satisfy the continuity equation. Okay. So, this is the continuity equation you need to solve when you are using Reynolds average Navier-Stokes equations. Okay. So, here you can see if you invoke this in this equation, what you will get. Okay. So, let us say this is your A and this is your B. Okay. So, from equation A and equation B, we can write. So, if you put this equal to 0, so first 3 terms will become 0. So, you will get del u prime by del x plus del v prime by del y plus del w prime by del z is equal to 0. What does it mean? It means that the fluctuating components satisfy the continuity equation. Now, let us consider x momentum equation. So, let us write the x component momentum equation, del u by del t plus del u by del x plus del u v by del y plus del u w by del z is equal to minus 1 by rho del p by del x plus we are writing this viscous term as nu nabla square u. Okay. So, now you invoke u is equal to u bar plus u prime, v is equal to v bar plus v prime, w is equal to w bar plus w prime, p is equal to p bar plus p prime. Okay. So, if you put it here, so you will get del of del t u bar plus u prime plus del of del x u bar plus u prime into u bar plus u prime, del of del y u bar plus u prime v bar plus v prime plus del of del z u bar plus u prime w bar plus w prime. Then in the right hand side you have minus 1 by rho del of del x p bar plus p prime and nu grad square u bar plus u prime. Okay. So, now you take the time average of this equation and invoke some properties which we have already derived. Okay. So, taking the time average of the above equation and putting f square bar is equal to f bar square plus f prime square. Okay. And also you write f g bar is equal to f bar g bar plus f prime g prime bar, and f prime bar is equal to 0. Okay. So, we will use these properties and we will simplify the above equation. So, if you put it, so you will get this as del u bar by del t, okay, del u prime bar by del t. So, this will become 0, okay, plus, so this you will get as del of del x u bar square plus u prime square bar, then you will get del of del y u bar v bar plus u prime v prime bar, then you will get del of del z u bar w bar plus u prime w prime bar is equal to minus 1 by rho del p bar by del x minus 1 by rho del p prime bar by del x plus nu grad square u bar plus nu grad square u prime bar. Okay. So, here you can see this will be 0 because time average of the fluctuating components will be 0, this will be 0 and this will be 0. Okay. So, now you can write this equation as del u bar by del t plus del of del x u bar square plus del of del y u bar v bar plus del of del z u bar w bar is equal to minus 1 by rho del p bar by del x plus nu grad square u bar, and we have 3 additional terms. So, that we are writing in the right hand side. Okay. So, you will see del of del x u prime square bar plus del of del y u prime v prime bar plus del of del z u prime w prime bar. Okay. So, you can see these are the new unknowns. Okay. So, these 3 terms are not 0 because we have already shown that your a prime g prime bar is not equal to 0. Okay. So, as these are not 0, so these 3 unknowns are appearing during the Reynolds decomposition due to the fluctuating components of the velocities. Okay. So, you can see these are known as Reynolds apparent stress. Later we will discuss in detail Reynolds apparent stress from the momentum transfer from the fluctuating components. Okay. So, now this we can write in non-conservative form. So, you can write del u bar by del t plus u bar del u bar by del x plus v bar del u bar by del y plus w bar del u bar by del z is equal to minus 1 by rho del p bar by del x nu, this you can write as del 2 u bar by del x square plus del 2 u bar by del y square plus del 2 u bar by del z square, okay. And these additional terms del of del x u prime square bar plus del of del y u prime v prime bar plus del of del z u prime w prime bar. Now, let us consider the energy equation, okay, and we will use the Reynolds decomposition in similar way whatever we have done for the x momentum equation. So, your energy equation is del t by del t plus del of del x u t plus del of del y v t plus del of del z w t, and right hand side you have only diffusion term, that is your alpha get square t. So, now you use u is equal to u bar plus u prime, v is equal to v bar plus v prime, w is equal to w bar plus w prime, and t is equal to t bar plus t prime. Okay. So, if you invoke and do the similar way, if you take the time average of these quantities, so you can write del t bar plus t prime by del t plus del of del x u bar plus u prime t bar plus t prime del of del y v bar plus v prime t bar plus t prime del of del z w bar plus w prime t bar plus t prime is equal to alpha grad square t bar plus t prime. Okay. So, taking the time average, okay, and using the properties, okay, you can write del t bar by del t plus del u bar t bar by del x plus del v bar t bar by del y plus del w bar t bar by del z is equal to alpha get square t bar, and you will get these three additional terms del of del x u prime t prime bar plus del of del y v prime t prime bar plus del of del z w prime t prime bar. So, these are again unknown terms. So, we have additional heat flux due to turbulent motion. So, now if you carry out the time averaging of y momentum and z momentum equation similar way, then we can write the Reynolds average Navier-Stokes equation as, so this is your continuity equation, this is the x component momentum equation, and these are the three additional terms. In y component momentum equation, these are the three additional terms. In z component momentum equation, these are the three additional terms. Okay. So, now these three equations you can write in tensor form as rho del u I bar by del t plus del u I u j bar by del x j is equal to minus del p bar by del x I plus mu del 2 u I bar by del x j 2 minus rho del of del x of u I u j prime bar. Okay. So, you can see this is the additional term, and energy equation also you can see these are the additional terms. So, if you see you can rewrite the momentum equation in tensor form as this, where del of del x j we have taken. So, mu del y bar by del x j minus rho u I prime u j prime bar. So, these right hand side quantity if we put as the total stress tau I j by del tau I j by del x j, then this stress term, okay, this is known as Reynolds stress or turbulent stress. So, we can write tau t is equal to minus rho u I prime u j prime bar, okay, is equal to minus rho. So, you can see that u prime square bar, u prime v prime bar, u prime w prime bar, here u prime v prime bar, v prime square bar, v prime w prime bar, and u prime w prime bar, v prime w prime bar, and w prime square bar. So, this is the Reynolds stress tensor, okay. And here you can see how many unknowns are there, because it is a symmetric tensor. So, there are 6 unknowns, okay, there are 6 unknowns. So, 1, 2, 3, 4, 5, okay, then 6, okay. So, these 6 unknowns, now we have to model to find these unknowns, okay. So, we can use Boussinesq eddy viscosity approximation, where this Reynolds stress, okay, is written in this way, minus 2 by 3 rho k delta I j, where k is the turbulent kinetic energy and delta I j is the Kronecker delta. Kronecker delta, you know that if I is equal to j, then its value is 1, otherwise 0, plus mu t, which is your turbulent viscosity or eddy viscosity. It is known as eddy viscosity. It is known as eddy viscosity, and in terms of the gradient of the mean velocity. So, you can write this Reynolds stress in terms of the gradient of the mean velocity with a unknown parameter eddy viscosity, okay. So, you can see now this mu t is unknown, okay. So, that you need to model. So, here turbulent kinetic energy is given by this expression, and if you see the total stress, then total stress will be your laminar stress plus the turbulent stress. We already know from the constitutive relation, okay, and this is the additional stress. So, that is your turbulent stress. So, this expression if you put it here and rearrange, then you will get in terms of the time average velocity gradient, and mu t is unknown. So, if you rearrange it, so you can see minus p bar plus 2 by 3 rho k delta I j plus mu t del u I bar plus by del x j plus del u j bar by del x I. So, you can see here only unknown is mu t. So, we have expressed the Reynolds stress in terms of the gradient of a time average velocity. So, this p bar plus 2 by 3 rho k you can write as p bar effective, and mu plus mu t, which is your dynamic viscosity, molecular viscosity, and this is your turbulent viscosity. So, these two together you can write as mu effective, okay. So, if you invoke in the tensor equation, so you will get in this form, where mu effective is your mu plus mu t, and this mu t is unknown, okay. So, this mu t is to be modeled, okay. In this regard, we will discuss about the turbulence intensity, okay. So, it is some measure about the turbulence, and you can see it is defined as the intensity of turbulence in a flow is described by the relative magnitude of the root mean square value of the fluctuating components with respect to the time average mean velocity. So, if I is the turbulent intensity, then it is root mean square value of this fluctuating components. So, 1 by 3 u prime square bar plus b prime square bar plus w prime square bar divided by the time average mean velocity. So, if you have a flow over flat plate, then it will become u infinity, and if you consider isotropic turbulent flow, so it is not having any directional preference. So, u prime square bar is equal to v prime square bar is equal to w prime square bar. So, you will get this intensity is equal to u prime square bar divided by your the time averaged mean velocity. So, you can see if this intensity is between 5 and 20, then you can say that it is a high turbulent case. If it is in between 1 and 5, then it is medium turbulence case, and if it is less than 1, then it is low turbulence case. And obviously, you can see for laminar flow this fluctuating components will be 0, then your turbulent intensity will be 0. So, when you numerically solve this Reynolds average Navier-Stokes equations, then you need to give the turbulence intensity at the inlet, okay, so that you can impose some turbulence at the entry. So, in today's class we started with the characteristic of the turbulent flows. Then we have discussed about two main characteristic of the turbulent flows. One is homogeneous turbulence, another is isotropic turbulence. Then we discuss about the Reynolds decomposition, and we started with the continuity equation, and using the Reynolds decomposition we have shown that mean velocity satisfy the continuity equation as well as the fluctuating components also satisfy the continuity equation. When we used the Reynolds decomposition for x momentum equation and taking the time average of this equation, there are 3 additional unknowns appear. So, these 3 unknowns are coming from the fluctuating components of the velocity, and if you have these 3 momentum equations u, v and w momentum equations, then obviously you will get 9 additional terms, out of which 6 are unknowns, okay. And you can write in as a Reynolds stress or the apparent stress, okay. We have also carried out the time averaging of the energy equation, and using Reynolds decomposition we have written the time average energy equation. There also we have seen there are additional 3 unknowns. Later we use the constitutive relation and the Boussinesq approximation for the Reynolds stress, and we have written the Reynolds average Navier-Stokes equation in tensor form in terms of the eddy viscosity, okay. So, you can see that here it resembles with the laminar flow Navier-Stokes equations, except one additional term in the viscous term. So, that is your Reynolds stress, and from the Reynolds stress using this Boussinesq approximation and the constitutive relation we have shown that you will get the effective viscosity as a summation of molecular viscosity and the turbulent or eddy viscosity. And here you can see only one unknown term is there, that is your eddy viscosity mu t. So, in later classes we will try to find this unknown eddy viscosity. Thank you.